Millions of engines, across multiple brands, failing. Not after 200,000 miles, not even after 100,000, but sometimes before 50,000. And here's the part that should worry you. It's not just one manufacturer. It's not just one defect. It's GM, Toyota, Honda, Hyundai, names that built their entire reputation on one single promise: reliability. Names that people trusted for decades. Names that parents recommended to their kids when buying a first car. Now tied to engine failures that nobody saw coming. So what changed? Because this isn't bad luck. And it's not coincidence. There is a pattern, a system, a cause that almost nobody is talking about openly. And once you see it, you won't look at modern engines the same way again. Let's go back for a moment, because to understand what's happening now, you need to understand what engines used to be. For decades, reliability meant one thing: simplicity. Naturally aspirated engines, big displacement, lower internal stress, fewer moving parts, fewer failure points, and most importantly, margin for error. Those old engines weren't perfect, but they were forgiving. You could skip an oil change, you could run them hard, you could neglect them slightly, and they would still run. Maybe not perfectly, but they ran. That's the world most drivers grew up in. That's the benchmark people carry in their heads when they buy a car today. And that's exactly why what's happening right now is so dangerous. Because modern engines are built on completely different principles. Smaller, more complex, more efficient on paper, but also more fragile in reality. Because today's engineering is not just about durability, it's about optimization. Fuel economy targets set by governments, emission regulations that get stricter every single year, performance per liter metrics that marketing departments use to sell cars. And that shift has changed everything about how engines are designed, built, and how long they last. Now look at the data, because the numbers are not lying. Rising recall numbers across every major manufacturer. Increasing warranty claims filed earlier in vehicle life cycles than ever before. Engines consuming abnormal amounts of oil at 30,000 miles. Turbo failures showing up before vehicles even leave the warranty period. Bearing issues. Timing chain and timing belt breakdowns. Rod knock appearing in engines that should have another 150,000 miles left in them. And this is happening across brands, across continents, different designs, different engineering teams, different manufacturing facilities. Same outcome. And that's the part that should stop you cold. Because when completely different engines, built by completely different teams, in completely different countries, start failing in similar ways, you're not looking at isolated defects. You're not looking at a bad batch. You're looking at a shared cause, something systemic, something baked into the direction of the entire industry. At first glance, each failure looks unique. A GM engine with oil consumption problems, a Toyota with timing chain issues, a Honda with excessive carbon buildup, a Hyundai with catastrophic bearing failure. Different components, different symptoms, different explanations from dealers. But when you go deeper, when you strip away the brand names and look at the engineering decisions behind each one, a pattern emerges. These failures are not random. They are connected, not by a single mistake, not by one bad engineer or one careless executive, but by a shared direction in modern automotive engineering, a direction that prioritizes certain outcomes at the expense of others. And the first major piece of that direction is downsizing. Engine downsizing. The idea that you can take a smaller engine, push it harder, and get the same power output as a larger, more relaxed engine from the past. On paper, it works. A 1.5-liter turbocharged engine can produce the same horsepower as a 2.5-liter naturally aspirated engine. The fuel economy numbers look great. The CO2 emissions look great. The marketing story writes itself. But here's what the numbers don't show. That smaller engine is working under significantly higher internal stress, higher combustion pressure, higher thermal load, higher stress on bearings, on rings, on the entire rotating assembly. And it's doing that with less material, less metal, less displacement acting as a buffer, less margin for error built into the architecture. Those old big displacement engines had something that doesn't get talked about enough. Slack, room to breathe, room to handle a slightly dirty oil filter, room to handle a hot summer day with the AC running full blast, room to handle real-world driving conditions. Modern downsized engines don't have that slack. They operate close to their limits by design. And over time, that stress accumulates. Components wear faster, tolerances open up where they shouldn't, and failures that might have taken 200,000 miles to appear now show up at 60,000. Then comes the second layer of this problem: turbocharging. Forced induction used to be reserved for performance cars, sports cars, high-end vehicles where buyers accepted the complexity as part of the package. Now it's standard. On economy cars, on family crossovers, on vehicles that people buy expecting simple, low-maintenance transportation. And turbochargers do increase efficiency. That part is real. But they also introduce heat. Enormous amounts of heat concentrated in one area of the engine bay. They introduce pressure spikes that older engine designs never had to handle. They introduce mechanical complexity with spinning components that can reach 200,000 revolutions per minute. And most critically, they create an absolute dependency on perfect lubrication. A turbocharger needs clean, high-quality oil flowing through it constantly. The moment that lubrication is delayed, or contaminated, or degraded, the damage begins. And in many modern engines, the turbo is positioned in a way that makes heat soak a real issue. Shut off the engine after a hard drive, and that turbo sits there, cooking, with no oil flowing, with heat transferring directly into the bearing housing, over thousands of cycles. That adds up. And one small failure in that system becomes catastrophic. Not just for the turbo, for the entire engine. Because metal particles from a failing turbo go straight into the oil system, straight to the bearings, straight to the cylinder walls. And at that point, you're not fixing a turbo. You're replacing an engine. But it doesn't stop there. Because the third factor is something most people never think about: oil viscosity. Modern engines are designed to run on thinner oils than ever before. 0W20, even 0W16 in some applications. Oils that flow faster when cold, reducing the brief period of dry start that happens every time you turn the key. And that does help fuel economy, measurably. Real-world numbers. The EPA tests confirm it. But thinner oil means less of a protective film between moving metal surfaces, less cushion, less margin, especially under high load, especially under high heat, especially in a downsized, turbocharged engine that's already running near its stress limits. Combine that with tighter manufacturing tolerances that are necessary to achieve the efficiency and power targets these engines are designed for, and you end up with a system that has almost no room for error. Any deviation from perfect maintenance, any contamination in the oil, any delay, even by a few thousand miles, past the oil change interval, and the wear rate accelerates dramatically. These engines don't just wear a little faster when neglected. They wear catastrophically faster, because there is no margin built in for imperfection. And then we get to the fourth factor, the one that might be the most uncomfortable to talk about: emissions. Modern engines are not designed purely for longevity. They are designed to meet regulatory targets, strict emission standards that have become the dominant force shaping engine architecture. And meeting those standards requires compromises, real compromises. Exhaust gas recirculation systems that route combustion gases back into the intake. Dirty, carbon-laden gases that contaminate the intake manifold, that coat the intake valves with thick deposits of carbon. On port-injected engines, fuel washing the valves kept them clean. On modern direct injection engines, there is no fuel touching the valves. So the carbon builds, cycle after cycle, year after year, until airflow is restricted, until valves can't seat properly, until performance drops and fuel economy suffers, and the engine begins to struggle in ways that are expensive to fix. That's not a manufacturing defect. That's an inevitable consequence of the design. And it's happening to millions of vehicles right now. Add to that the complexity of modern after-treatment systems, particulate filters, selective catalytic reduction, systems that add back pressure, systems that require specific operating conditions to regenerate properly, systems that, when they malfunction, create cascading failures throughout the powertrain. All of it adding stress, all of it reducing the long-term durability of engines that are already operating closer to their limits than any generation before them. And here's the part that changes everything. This is not a series of mistakes. This is not incompetence. This is a direction, a deliberate, industry-wide direction where efficiency is prioritized over longevity, where engines are optimized for regulatory compliance cycles, not for decades of real-world use, where the decision was made, consciously or structurally, that a modern engine doesn't need to last 300,000 miles. It needs to pass emissions tests. It needs to hit fuel economy targets. It needs to perform well in the first 100,000 miles. After that, it becomes someone else's problem. And once you understand that, everything starts to make sense. The reason it's not just one brand is because every brand is chasing the same targets, the same EU regulations, the same EPA standards, the same CAFE fuel economy requirements in the United States, the same global pressure to reduce CO2 output across the entire fleet, which means every manufacturer makes similar compromises, different designs, same constraints, same direction, same outcomes. GM didn't fail because GM is careless. Toyota didn't fail because Toyota abandoned quality. Honda and Hyundai didn't fail because their engineers stopped caring. They failed because every one of them is operating inside the same regulatory and market environment, an environment that rewards efficiency in the short term and doesn't penalize durability failures in the long term, at least not fast enough to change the direction. Now bring this back to you, because this is not theoretical. This is practical. If you own a modern vehicle, built in the last 10 to 15 years, with a turbocharged, downsized engine, your margin for error is smaller than you think. Engine lifespans that used to reach 250,000 miles without major intervention are now being cut short at 80,000, 100,000, 120,000. Repair bills that used to be manageable are now catastrophic. Because when a modern engine fails, it often fails completely. Not a gasket, not a sensor. The engine, and what used to be minor neglect, that missed oil change, that slightly extended service interval, is now a potential death sentence for your powertrain. What used to last decades may not anymore, not without a completely different approach to maintenance. So here's what you need to watch for. Early oil consumption is the first warning sign. If your engine is using more than a quart every 3,000 miles, pay attention. That is not normal. That is a signal. Unusual noises at startup, ticking, knocking, or rattling that disappears after a minute of running. That brief period before oil pressure builds is when the most damage occurs. And if components are already worn, you'll hear it. Turbo lag where there wasn't any before, or a high-pitched whining from the turbo that changes with RPM. These are not sounds to ignore. These are early indicators of bearing wear inside the turbocharger. Check engine lights related to timing or oil pressure. These codes are not inconveniences. They are emergency signals. And ignoring them, even for a few weeks, can turn a $500 repair into a $5,000 engine replacement. So what can you actually do? The most impactful change you can make right now is shorten your oil change intervals. If the manufacturer says 10,000 miles, consider 5,000 to 6,000, especially if you drive in hot climates, especially if you tow or haul regularly, especially if your engine has a turbocharger. Use the highest quality oil your engine specifies, full synthetic, meeting the exact viscosity rating required, not a close alternative, the exact specification. Because in a system with no margin for error, the quality of your oil is one of the few variables you actually control. Warm your engine gently before pushing it hard. Modern engines reach operating temperature faster than older designs, but the first few minutes of cold operation are still when wear is highest. Avoid full throttle pulls until the engine is fully warm. Your turbo will thank you. Maintain your cooling system. Keep coolant fresh. Watch for any signs of overheating, because heat is the enemy of every failure mode we've talked about. And if you haven't had your intake valves inspected on a direct injection engine with significant miles, consider a walnut blasting service. It's not cheap, but it's significantly cheaper than an engine. If you're in the market right now and shopping for a vehicle, think differently about what you're evaluating. Don't just compare horsepower numbers. Don't just look at fuel economy ratings. Look at the engine architecture. Naturally aspirated engines, where they still exist, carry far less risk than turbocharged alternatives. Larger displacement engines, even if slightly less efficient, have more margin built in. Proven platforms with years of real-world data behind them. Not first-generation designs that are still being sorted out. Look at the oil specifications required. If an engine demands 0W16, understand what that means. Look at reported issues in owner communities, because the dealers won't tell you. The manufacturer won't advertise it. But the owners know. And in today's market, reliability is no longer guaranteed by the badge on the hood. It must be actively selected. And this trend is not slowing down. Engines will become even more complex in the years ahead, even more optimized, even more dependent on perfect conditions. And as electrification accelerates, manufacturers are allocating less engineering resource to long-term combustion engine development. The investment is shifting, which means the engines being sold today may be among the last generations that receive serious durability engineering attention. After that, it's maintenance of an aging platform in a world that has already moved on. So here's the truth. Modern engine failures are not accidents. They are consequences. Predictable, logical consequences of a system designed around efficiency over endurance, around regulatory compliance over real-world longevity, around short-term performance metrics over long-term owner experience. And once you understand that, you stop expecting old-school reliability from new-school designs. You stop assuming that a Toyota badge or a Honda badge or any badge means what it meant 20 years ago. You adapt. You maintain more carefully. You pay more attention. You make smarter decisions when you buy. Because the difference between the driver who loses an engine at 90,000 miles and the driver who gets 200,000 out of the same vehicle is rarely luck. It's knowledge. It's habits. It's understanding the system you're working with. And the drivers who learn this early are the ones who avoid the most expensive mistakes.